Welcome to another riveting episode. I'm sorry I've been gone for a while. I hope I didn't disappoint my millions of fans. um, so yeah, if you've watched my videos, you know that they're pretty scattered, right? 1 minute I'm talking about prime numbers, 1 minute I'm talking about quantum mechanics to unbounded infinities, etc., etc. Because that's just the way my brain operates. I'm so busy, my ideas are just constantly moving around. And I've been spending the last little bit of time actually organizing these ideas. And there is a reason why I've been focusing on these certain things, because they're all kind of connected. And I've actually started taking everyone's advice and actually started writing real papers that I have submitted. They're really boring, they're technical, definitely not my kind of thing. All right. Now, this video is actually kind of not flashy, you know. I'm not going to introduce a theory of everything or I solve this thing or anything like that. It's pretty much just cleanup. And even if my papers do get accepted, I'll kind of be seen as a buzzkill, because I'm kind of going to just ruin a bunch of people's crazy ideas out there. So it may not be accepted earlier on, but maybe later on I'll be that guy. So let me start out with something simple, right? We have a dot. Every coordinate system we use has this dot in the middle. We need a place to start, so it makes sense to have it there. But here's the uncomfortable question we almost never ask. If we're going to put a special place in the middle, what exactly is it supposed to represent? Because in practice, the point is us, right? We're the ones making the measurement, whatever this is. The observer, the measurement, the place where information shows up. And as soon as you say observer, all of a sudden it becomes woo, 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 but you can't deny that placing a zero in the middle of a coordinate system is very special, right? Zero does not act like anything else. Now, I'm going to touch on Copernicus here, right? So before Copernicus, we thought the Earth was the center. He came along and said, no, the sun is the center. And all of a sudden, one idea became right, and this idea became wrong, which is already wrong in itself. Having us at the center of the universe is just as valid as having the sun at the center of the universe, or having our galaxy at the center of the universe. There is no special center in the universe. Therefore, any coordinate system you pick is just as valid as any other, right? The only reason we picked the sun at the center of the solar system is because the math was easier. But just because the math is easier, that doesn't make it more valid or right. It's just more convenient. But the right thing that cosmology got right is that once we started changing the center point, we automatically jumped to the conclusion that there is no special point. Unfortunately, some other paths of knowledge we took didn't jump to that conclusion right away. Every kind of thing, math, cosmology, everything is going at a different order and pace to get to that, right? Because once again, we put zero in the middle of our coordinate system. We've made the center very special. So 1 minute we're saying the observer doesn't matter. The next minute we're saying build everything around an observer. There's no special place. And yeah, it gets very confusing because we're not thinking about that. And if you start thinking about that, everything else starts falling into place. Okay? This is a problem with the order, what I call the order of discovery. Right? We learn how to describe space long before we learned how limited observation actually is. And once that order is locked in, it's incredibly hard to see past it. So this dot isn't the universe. It's a point of view. And if we're serious about understanding anything deep, time, quantum mechanics, infinity, we need to understand what this point is and what it can't see, what its limitations are. So once you accept that this dot is a point of view, the very next thing you're forced to draw is your past light cone. This part is actually pretty standard physics, nothing controversial here. In relativity, the only things you can observe right now are events whose light has had time to reach you. Everything else is either too far away or casually disconnected from you. So already you can see that reality for the observer is filtered. What you experience as the universe is not actually how the universe is. It's the universe as it used to be. There's always a delay in what we see. It's like lag in a computer. Even the light hitting your eyes right now left its source in the past, and the further away something is, the further back in time you're actually seeing it. This cone isn't geometry, it's actually a limit of knowledge. It's not just, a drawing, it's real. Now, if we start to accept these things, things start to get very interesting. General Relativity does an incredibly good job of describing how things in this cone bend, stretch, distort, gravity, curvature, horizons. All that is in here. GR tells us information from the past, which reaches the observer. But notice what it doesn't tell us. It doesn't tell us anything about what hasn't happened yet. It doesn't tell us what's behind the observer. That's not a flaw, it's a feature. Relativity is a theory built entirely from the past-facing point of view. It assumes that physics is reconstructed from what has already occurred, which works beautifully. The math is great, until it doesn't, right? Because the moment you start asking questions about measurement, probability, or quantum behavior, you're suddenly forced to talk about things that haven't resolved yet. They haven't entered your cone. And that's where the picture starts feeling incomplete. So at this stage, we've done something very specific. We've drawn a universe where the observer sits at a privileged point right there. All knowledge arrives from the past, and time is treated as something we reconstruct after the fact. And that setup works out so well that we forget it's a setup at all. It's just how it's set up. Now I want you to take a moment to do a thought experiment with me. All right, forget the diagram for a second. Imagine you freeze, not the universe freezing, just you, the observer. Okay? No motion, no interaction with the universe, no updating, just you paused in time. The universe doesn't stop. Light keeps moving, events keep happening and interacting with each other, but you are no longer participating in them. You're no longer entangled with what's going on around you, and something strange will start to happen. Everything you thought was solid begins to lose definition. Objects don't have sharp positions anymore. Events don't have clear outcomes. The world doesn't disappear. It becomes fuzzy and probabilistic. Because without interaction, without updating your system, there's no way for things to settle into a definite facts for you. Reality hasn't broken, your access to it has. And that fuzzy probabilistic description, the one where outcomes aren't fixed until interaction happens, sounds a lot like quantum mechanics, right? So if the past light cone is everything that can reach us, then we have to ask the uncomfortable question, what's back here? Behind the observer. Because physics almost never draws this part. We talk endlessly about the past here, curvature, horizons, and all that stuff, but the future treated like a blank page that somehow hasn't happened yet. But that's already an assumption. Here's the key shift. Time isn't something we're standing in and watching flow forward. It's something we're moving through. And we're not facing forward, right? We're looking this way. We're facing backward in time. We're going through time facing backwards. Everything you've ever observed, literally everything, is behind you in time. You've never experienced the present directly. By the time information reaches you, it's already old. The now is I can't even say the word, inaccessible. It's a boundary, not a moment. So from your point of view, the universe is reconstructed from past data while you're continuously moving into something you cannot see. Which means this arrow isn't empty, it's just unobserved. Now here's where a lot of confusion comes from, right? When physicists say the future doesn't exist, what they usually mean is we don't have access to it. But that's an epistemic statement about knowledge, not an ontological one about reality. And mixing those two up causes a ton of problems. Because if the future truly didn't exist in any sense, then probabilities would be meaningless. You can't assign probabilities to nothing. You assign probabilities to incomplete information about something real, but unresolved from your point of view. So instead of thinking the future as not there, it's more accurate to think of it as it's behind you, it's unseen, it's unmeasured. It's just not, it's unresolved. Now let's connect this back to the freeze thought experiment. When you stop interacting with the world doesn't vanish, it turns probabilistic. Not because reality breaks, but because your coupling to it does. You're not connected to it anymore. Measurement isn't magic, collapse isn't mystical. It's just what happens when an observer re-enters interaction with something they were previously not coupled to. And that tells us something very important. Quantum mechanics isn't describing a weird kind of reality. It's describing reality from a future-facing problem, from the side of things that haven't yet stitched into the observer's past. Now, when you adopt this idea, relativity is past-facing reconstruction of the universe, and quantum mechanics is some future-facing uncertainty. You realize there's just two perspectives of the same universe. And once you see that these theories don't get along, it starts to look a lot less like a fundamental conflict and more like just a coordination problem between two points of view. Now, before this starts sounding like I'm about to drop a grand unifying theory or anything like that, no, I'm not. This is what I'm saying. I'm just a buzzkill, really. I'm not tearing physics down. I'm not proposing new forces or rewriting equations, or I'm literally just cleaning this up, giving it a point of view that makes it make sense. I'm saying maybe the reason we have so many models that work but don't seem to agree is because they're all describing the same structure from different observational orientations, different angles of the same thing. And the real question isn't which model is right, it's what is the underlying structure that all these viewpoints are projecting from. And that's where things actually get interesting. And that's also where I'm going to stop, because in the next video we're going to walk straight into that same conclusion from a different angle, but from a completely different corner of academia. And when two unrelated fields start pointing in the same problem, there's usually a sign that we're not chasing noise anymore. So once you accept that all observers are always reconstructing the universe from incomplete information, something else clicks into place. Perspective isn't like a nuance, it's how everything works, it's the whole game. Every observer has their own light code, their own delays, their own resolution limits. So every observer builds a slightly different version of reality, not because reality is subjective, but because your access to it is. And here's the part that sounds obvious, but almost never gets taken seriously enough. If you change your point of view, you change what looks fundamental. From one point, there's a view of particles everywhere, fields look abstract. From another, fields look real, but particles look like bookkeeping. From another, geometry is primary. From another, information is. And all of these models work. And that should bother us, but not because one of them is wrong. It should bother us because they all work too well. That's usually a sign that they're shadows of the same thing. So instead of asking which model is correct, we should be asking, what are all these models projections of? Now this is where I like to use the word omniverse. Oh, turn that on. Omniverse. I know that word gets abused a lot, so let me be very clear. I don't mean multiple universes, many worlds. I don't mean branching realities, sci-fi stuff. I mean the total structure that exists independent of any observer's access to it. The thing that looks like space-time from one angle, like probability from another angle, like geometry from another, and like information from yet another version perspective. Every time we discover a new theory, we act like we found something fundamentally new. But maybe all we really did was rotate the camera angle, right? Or move over here or over here. And this is where order of discovery really matters. In cosmology, we learned pretty early that there's no special place, no center, no privileged location. And math forced us into that, right? It made the math easier. But in other areas like math, physics, even logic, we quietly kept special points everywhere. Kept a zero, an origin, a preferred frame, even a now, right? Not because they're real, but because they're convenient. Any convenience has a way of turning into dogma if it's not careful. We have discovered if we had discovered the whole structure first, the whole Omniverse, the continuum, the infinity, whatever you want to call it, and then discovered the limitations of the observer, the limited slices inside of it, a lot of the current paradoxes we have now would have never formed. They're artifacts of perspective mistakes. And that's the pattern you'll start seeing everywhere once you look for it. In different theories, different languages, it's same underlying structure. That's not because physics is broken. We're stuck because we keep mistaking viewpoints as fundamentals. And once you start separating those two, you don't get a flashy new theory. You get something much quieter and much more unsettling. You realize the universe probably isn't hiding from us. We're just standing in the wrong place, facing the wrong direction, asking the wrong kind of questions. And that's exactly where we'll pick up next time, from a completely different field, to show that this problem isn't just in physics. We do it in everything. Thank you.